For a very long time, humans have imagined what life may be like on other worlds. Thanks to the James Webb Space Telescope, the most powerful telescope in existence, we may finally have some answers. In the end, the answer to that question can be explored while keeping an eye on our closest neighbor, the Proxima Centauri star system, which is only 4 light-years away. Scientists have noticed some peculiar anomalies from one of the planets in the system. These anomalies are referred to as artificial lighting, which has been the most perplexing discovery within the scientific community. What are they? Do these lights suggest that intelligent life exists on the planet? Join us as we explore the James Webb's terrifying discovery of city lights that could change everything. The only life that we are currently aware of is on Earth. Since the beginning of civilization, people have questioned whether there is life elsewhere in the universe. To carry out such an interstellar search, American astronomers Thomas Pearson and Jill Tarter launched the Pursuit of Extraterrestrial Intelligence SETI project in 1984. The goal of the non-profit organization is to gather spaceborne radio signals. Radio waves can travel farther and are, therefore, more likely to be picked up by the 42 telescopes that make up the unique Allen Array in the Californian Cascade Mountains. However, in the last 30 years, no evidence of an alien presence has been discovered. Following that, the James Webb Space Telescope's successful launch aided in the investigation of a variety of undiscovered planets orbiting distant stars. As the largest telescope in the world, floating roughly 1 million miles from Earth and equipped with extraordinarily sensitive detectors, it has the potential to uncover significant findings. 20 years ago, there were no known planets beyond our solar system. But since then, more than 4,000 exoplanets have been discovered orbiting other stars. NASA claims that the universe contains trillions of exoplanets. The first evidence of life beyond our solar system could be found on other planets. The Galileo spacecraft on its route to Jupiter flipped its gear back toward Earth and found a definite indication of the presence of plants, detecting the vegetation red edge, VRE biosignature, a mix of red and infrared light reflected by plants. For instance, a planet like Earth covered in a jungle should have a robust and easily detectable VRE signal. The JWST will measure the VRE of far-off Earth-like planets in the habitable zone around stars, which could provide important signs of life in an exoplanet's atmosphere. When sunlight crosses a planet's star, the JWST may be able to detect it as it enters its atmosphere. The missing wavelengths would then be discovered via spectroscopy, as atoms and molecules in the atmosphere absorb specific wavelengths, creating a characteristic fingerprint that the JWST can recognize. This method may be used to determine the composition of the atmosphere and whether or not it can support life. Life could exist on Earth-sized planets with atmospheres similar to our own, characterized by a predominance of nitrogen, carbon dioxide, and oxygen. By looking for things that don't typically appear naturally, one may be able to detect technological life. For example, chlorofluorocarbons, CFCs, which are generated for use in cleaning and refrigeration products, would likely be noticeable to aliens observing Earth's atmosphere from a distance. If the JWST found CFCs in the atmospheres of exoplanets, that would be a clear indication of civilization. However, life on exoplanets might not resemble life on Earth at all. Sometimes even earthly life forms, like species of extremophiles that can survive in environments where other living things would perish, can seem alien. This group of organisms, primarily bacteria, can withstand extreme conditions, such as heat up to 250 degrees Fahrenheit or strong acid with pH levels below 1. Since planets like Earth are more likely to support life than those experiencing extreme temperatures or acidic conditions, it would be wise to start with those first. Prime candidates could have temperatures that make it possible for liquid water to exist on their surfaces and orbit a stable star. Our Sun is classified as a yellow G-type star. These stars are less common and typically have shorter lifespans. However, in our universe, planets orbiting red dwarf stars, more frequent and with lower temperatures and luminosities than the Sun, are more likely to be studied. This extended time frame enables the development of life and evolution into complex organisms. Around 40 light-years away from Earth, the TRAPPIST-1 planetary system will be the subject of the JWST's first mission. It is centered on a serene red dwarf star with 7 rocky planets the size of Earth. 3 of these rocky planets, in the so-called habitable zone, might have liquid water on their surfaces. Despite its smaller and colder mass compared to our Sun, the TRAPPIST-1 star radiates light that is similar to that of Earth. Due to their planet's close orbits, the best opportunity for people to see city lights outside the solar system is with the red dwarf star Proxima Centauri. Proxima Centauri is 4.25 light-years away from the Sun and about 600 times fainter than the Sun. A planet must be 20 times closer to it than Earth is to the Sun to support life based on liquid water. In August 2016, astronomers discovered a planet with 1.3 Earth masses in this habitable region, a Goldilocks-like zone where the light intensity is just right to melt water. Proxima B orbits Proxima Centauri, but it is possible that Proxima B is an airless, lifeless planet. Given that it orbits its red dwarf star at a distance of only 4.6 million miles, this close orbit exposes it to strong solar winds that could completely destroy its atmosphere. However, Proxima B does receive enough sunlight for temperatures and liquid water comparable to those found on Earth. Because of how close it is to the star, Proxima B is thought to be tidally locked, always showing the same side to the star, much like the Moon does in relation to Earth. Proxima Centauri has about 18% of the Sun's mass and burns much less brightly than expected for a planet so near to its star. At just 5% of the apparent distance between Earth and the Sun, Proxima B could be a red-hot cinder. Liquid water could remain on Proxima B for as long as the planet has an atmosphere to retain heat, since the total amount of energy it receives from its star is only 65% of what Earth receives. However, the planet is not especially friendly to life. It is most likely tidally locked, meaning it always faces the same direction toward the star, producing permanent day and night sides with significant temperature variations. The planet also receives 100 times more high-energy radiation than Earth does, including ultraviolet light and X-rays, due to its proximity to Proxima Centauri. Proxima B is also bombarded with high-energy particles during stellar flare-ups. Unless it has a shielding magnetic field comparable to Earth's, the conditions for life there may be extremely challenging. Life may not be favorable under certain realistic conditions, but Proxima B could potentially be a more pleasant world. Sadly, models indicate that the climate of tidally locked planets may be susceptible to rapid collapse due to volatiles freezing on the night side. Our planet's atmosphere can be replenished by volcanic activity, and for planets with strong magnetic fields, this atmosphere is less likely to escape. However, since we don't know anything about Proxima B's volcanic activity or the magnitude of its magnetic field, we can only guess whether or not the planet has an atmosphere. Nevertheless, because an atmosphere assumes the presence of seas, and the two taken together presuppose the existence of life, we are desperate to know if Proxima B has a sophisticated civilization. If it does, it might have solar panels covering the day side to generate electricity to light and warm the night side, which would otherwise be too cold and dark for comfortable habitation. The discovery of Proxima B has triggered a race to determine if it crosses its star from Earth's perspective. These are the phases of the stars that scientists would be able to determine via transits. By observing transits, scientists could determine the planet's size and mass, allowing them to calculate its density and validate its rocky makeup. This would provide information on the materials that make up those rocks. During a transit, starlight passing through the planet's atmosphere might reveal the nature of its composition. However, the likelihood that the orbit is in the right alignment for scientists to observe a transit is merely 1.5%. Additionally, the star's propensity to flare complicates matters. Astronomer David Kipping of Columbia University states that stellar heat causes a rocky planet to absorb sunlight and re-emit it as infrared light. However, rocky planets produce a distinct type of infrared radiation compared to stars like Proxima Centauri. Additionally, the James Webb Space Telescope, JWST, was created specifically to study infrared light. The infrared heat signature of Proxima B is key to determining the planet's atmosphere. The JWST's strong focus on the infrared spectrum could even allow it to observe city lights on Proxima B's night side, even if they are as faint as those on Earth. The JWST could detect artificial illumination, as long as it falls within a frequency range 1,000 times smaller than the star's light. Proxima B's day side may be heavily coated with solar panels, reflecting starlight. Since Proxima B is tidally locked to its star, day and night are identical, with cool evening lows following daytime highs. However, the temperature difference between day and night depends on whether or not the planet has an atmosphere or oceans to help distribute heat. If Proxima B lacks an atmosphere, its day and night temperatures will differ significantly. The day side would emit all of the energy it receives from Proxima Centauri as blackbody radiation, while the night side would resemble a frozen hell. If the temperature difference is less pronounced, we can infer the presence of an atmosphere. Conveniently, the JWST will only need 11.2 Earth days to measure the infrared radiation from Proxima B's two faces after it completes an orbit. If Proxima B has an atmosphere, the next step will be to analyze its composition. The presence of gases like oxygen, water vapor, and methane could indicate habitable conditions, if not actual life. However, detecting these gases requires successfully capturing starlight as it bounces off or travels through the planet's atmosphere, a difficult task that only the JWST can closely examine for the nearest potentially habitable worlds. The JWST was not specifically built to search for extraterrestrial life. It is primarily limited to tracking changes in atmospheric concentrations of methane, carbon dioxide, and water vapor. Additionally, the JWST is unable to detect the presence of molecular oxygen, a key sign of life, even though some gas mixtures may suggest biological activity. The Extremely Large Telescope (ELT), scheduled to begin operations in the mid-2020s, will be the first ground-based observatory capable of conducting a thorough atmospheric investigation. The JWST may be able to detect ozone, but until telescopes like the ELT are operational, JWST data will give us insights to consider for the next decade. Future space telescopes may use advanced techniques to block the overwhelming brightness of a planet's host star, allowing astronomers to analyze the way light reflects off the planet. This is similar to shading one's eyes to see a distant object more clearly. Space telescopes might achieve this by using internal masks or large, umbrella-shaped satellites. Unfortunately, most gases produced by terrestrial life can also be created through non-biological processes. For example, methane is released by cows, but it can also result from sunlight and volcanic activity breaking down water molecules into hydrogen and oxygen. When searching for alien life, astronomers will likely encounter false positives. Therefore, they must develop a deep understanding of a planet's geological and atmospheric processes to determine whether its conditions could support life. The next wave of planetary research may provide the compelling evidence needed to establish the reality of extraterrestrial life. The James Webb Space Telescope's early data offers a preview of significant advancements to come. If life exists elsewhere in the cosmos, it would answer one of science's most profound questions. Life may be abundant throughout the universe, or we may be completely alone, trapped on a solitary planet in deep space. Either scenario would have major philosophical and psychological implications for humanity. The search for extraterrestrial life has fascinated humankind for centuries, inspiring countless stories and theories. As technology advances, our understanding of the cosmos expands, revealing new possibilities for life beyond Earth. Space telescopes like the JWST not only enhance our ability to detect distant planets but also allow for detailed atmospheric analysis, helping scientists identify potential biosignatures. Furthermore, exoplanet exploration fosters global scientific collaboration. International partnerships in space research promote knowledge sharing and resource pooling, increasing the likelihood of significant discoveries. These efforts also enhance public interest and engagement in space exploration, sparking curiosity and imagination. Finally, the philosophical implications of discovering alien life force us to deeply reflect on our existence. Would finding extraterrestrial civilizations change our understanding of life's purpose? Such questions challenge us to rethink our role in the universe and our relationship with our home planet. As we refine our technologies and methods for exploring the stars, each new discovery brings us closer to answering the age-old question: are we alone in the universe? The journey ahead is filled with potential, driving the quest for knowledge and understanding beyond our earthly confines.